All right, so 1, 2, 3. Okay. All right. So we were here, we were talking about software attestation. We said that essentially we're going to have two pieces of code, a verification code and an application code. The idea is that we're going to create what we call a self-checking attestation, where the verification code, we're going to check the verification code itself, but the verification code also does the checking. So that's why it's kind of what's called self-checking. And then what we do is that we check the hash of the verification code as well as the time it takes to run the verification code. And the idea is that the adversary cannot lie about both. So if something changed in the verification code, the code would look different and the hash will result in a different number. Or if the adversary doesn't change the verification code and tries to kind of like move the control flow to somewhere else in the program, that will cause an additional jumps or different activities that will change the time. So these kind of dual behavior allows us to achieve the level of security that we want to achieve. So the full process will look like this: that the verifier send a challenge, start a timer. So the timer starts here. Oops. Two. Turn my this on. I think it's on. So. Okay. Yeah. Okay. Sorry about that. So the verifier send a challenge, which is a nonce, a number C, starts the timer here. Then the prover, inside the prover's memory, there are three things. There is the verification code, there's the application code, there might be other things as well. Then during this process, essentially the verification code is comprised of three important things. There is the hash function. Sorry, there's a hash function. There is the initialization function, which essentially you can think about like, getting the values of the nonce and all. And there is a communication function, which is basically the functionality to kind of talk to the verifier, sending and receiving the results. So the verification function does these things, does the hashing and initialization and communication. At this point, we're going to send the hash of the verification code and the C. So essentially, C allows us to eliminate the replay attacks. And then at this time, the verification code can also hash the application code and send that as well. We can send these together or as separate two messages. Then at this point, the verifier will check these hashes, the hash of the verification code and the hash of the application. If these two hashes are the correct hashes, based on this C, and this time is the correct timing, that is like, based on some expected value, then we're going to trust this system. We're going to trust the verification code and we're going to trust the application code. And once we trust these two, we can then pass the control to the application and run the application, or just know that the status of the device is not modified. As I said, this is what we call a self-checking technique, that essentially instead of checking the memory, we are checking only part of the memory, which is the verification code. And once we trust that and use that, the timing, then we call this a dynamic root of trust, or DRT, which means that now we trust the verification code. We show that the verification code is also running correctly. So anything that verification code calls will be kind of bootstrap into our trust, right? So we're gonna basically kind of like, saying that, okay, now we trust the verification code. Now, if the verification code, for example, call another function and check the hash of that, now we trust that application as well. If that application calls another application, we trust that as well. So we created this chain of trust on our system, okay? So what are the things that we do in order to make sure that, the timing is not, we ensure that if the adversary kind of move the code to some other part of the program, this timing will change. We're going to use these two tricks. So essentially, if you think about the way that the adversary can launch this attacks is one of these four options. So, PC, if you remember, was the program counter. DP is the data pointer, is the place that we read the memory from. So if the verification function is in the place that we are running the attestation and the verification function hasn't been modified, that's the original scenario that we want to achieve, right? So the PC and DP and verification function all in pointing the same place, right? So this is the no attack version, okay? So now think about the various ways of the adversary manipulating this process. One option is that the adversary copies this verification function somewhere else, okay? And run their malicious function. So the PC is pointing to the malicious function. So when we are requesting the attestation, the malicious function is the one that is running. But when it's doing the hashing is run on another pointer, like it's reading other addresses in the program, okay? So it's reading different addresses, which is pointing to the correct verification function. The second thing that can be done is essentially we don't change the position of verification function, but the malicious function is running at some other place. In other words, the PC is not the same PC as before. Instead of running the verification function as its correct and original location, we are running our malicious function at some other place. The DP is the same DP that we are expecting, but the malicious function is at some other place. And of course, the fourth option is that neither the PC nor the DP is at the right place. So we run the malicious function at some other location in the program, and the verification function is at other places of the program as well. The fourth one is like the most unrealistic, like, there's no point of doing this. So the adversary probably either do B or C. So how do we prevent either of these two from happening? The key idea is that your hash function should include both the value of PC and the value of DP. So essentially, we don't just read the value that is stored in the memory and hash that. The thing that we usually do is that we hash this value, basically, and memory DP, okay? Sorry. So this is what we're going to hash, okay? So we're not going to hash just the memory content. We hash the memory content, and the address of that memory content is provided by the pointer, but we also include both DP and PC. The reason that we include both is that we want to make sure that the address that we are reading from is correct. That gives us the DP. And we want to make sure that the function, the instruction that we are running is also from the original instruction that we know. That's why we include PC. Okay, so we include three things in our hash functions. And this way we guarantee that only this will work. Otherwise, if the adversary does anything other than this, they have to do it dynamically. So essentially, anytime that they have to kind of like jump back and forth, and jumping back and forth in order to achieve correct DP, PC, and hash will result in significantly higher time. So either the adversary will have to accept the fact that the hash is not correct, or if they want to maintain the correct hash, they have to continuously have the right DP and PC, which means that now the time has to go up, right? So for example, the adversary can does something like this, that V is here, the malicious code is here, and then originally PC was here. So they need to kind of like, every time that they need to compute the hash, they have to jump here, run one instruction here, and then somehow jump back here and then continue. So this will result in lots of jumps or a lot of changes or they have to decompress. There are like lots of things that the adversary can do in order to achieve this, but all of them will result in just more computation, which not going to pass the timing requirements of the attestation. Okay. The other option, other than instead of like doing the verification function and then doing the dynamic root of trust, is that if you actually do that attestation on the entire program memory, that's also another option. So this way, the adversary cannot hide its own code, assuming that there is no other place in the program memory for the adversary. Although this has been shown that it's not the most efficient or the most robust option, because, for example, people have shown that the adversary can copy things into the data memory or some other parts of like, flash or ROM. So people have shown that this may not be the most effective option. And as I said, and one thing that the adversary can always do is that, like, do the attestation here, but then move the code here. But again, that requires a very time-consuming memory copy, which is not going to pass the timing. So again, if I use the timing and use the hash NDP method like that, wouldn't work. Questions here? Great. So there are a few considerations for attestation. The main one is that what sort of hash function should we use? Should we use a hash, just a secure hash? Should we use just an ad hoc hash, like a checksum function? Should we use a MAC, which is a keyed hash? There are various different papers doing it differently. Actually, later on, I'm going to show you a recent paper that we actually published, and we talk about why we can go by hash and then only use MAC at the end. The main difference between a hash and a MAC is that MAC can be only done by a trusted entity who has access to the secret key, versus hash can be done by everyone. So that means that the adversary might also have access to the secure hash. The second thing that is very important is that if you are relying on the fact that verification, function, and we kind of time the operation of verification function, the verification function should be optimal, right? So there shouldn't be an obvious way of optimizing it. Specifically, the hash function or the MAC function should be optimal. The good thing is that these are the functions that has been researched on for a very long time. So the entire crypto community is like spending a lot of time on optimality of their hash functions. So there are actually theoretical guarantees for optimality of, like, let's say, a hash function. They actually, for example, if you remember, we talked about like HMAC and PMAC. People have shown that these functions cannot be parallelized. So if you chain them together, the adversary cannot, let's say, like read two instructions at the same time and compute the hash. They have to read the first one, update the hash, read the second one, update the hash. So there are, proofs for optimality of the system that way. Yes.
Can't you just clock it twice as fast then? Something else?
You can change hardware. Yes, you can change hardware. But for example, the idea is that you have an Arduino, right? So, and you have to run this assuming that you have the fastest system, like the fastest clock. So I don't know, if you run at 16 megahertz, you cannot go beyond that anyway, because the system is just restricted on that sense. But yeah, if you run twice as fast, if you change the hardware somehow, then this no longer is true. And then, of course, this is something that we kind of discussed last time. Knowing the exact timing is difficult, because the system is also, there are other things that might negatively impact the timing. The most critical one is the network. So if, for example, the verifier and the prover is sitting on two sides of a network, so this communication and this communication has some delays, right? So if you remember, we talked about this when we were talking about distance bounding as well. And I told you that if there is like a tiny bit of delay, like a delta, then or an epsilon, then this epsilon, then the adversary can basically remove this and add it to their computation, right? So this network communication, both the sending and the reception, should have very minimal jitter. If it's a high jitter network, that every time that you're sending, there might be a huge amount of unknown amount of delay, then the adversary can find a faster network, a lower jitter network, and use that time in their benefit. So that's very important that the security of this method relies on the fact that your network behavior is very deterministic. It's okay that this delay is high. It just has to be deterministic. That's the important thing. So it doesn't need to be like a low overhead, like a low delay network. It can be like seconds or milliseconds, but it just have to be very deterministic. So every time I send and receive, I have to get the same exact time. Yeah, and then as I said, so like that obvious limitations of this system is that if the T send is that this is the time it takes for sending or receiving the request is much, much bigger than the T attack, then the adversary will use this to in their own benefit, right? So the design, so these are kind of more of the physical limits of a software attestation. Good thing is that, for example, for wired networks, or for home networks, for like, local networks, this doesn't happen that much. So usually you get a fairly stable network latency. But if you're talking about a truly remote attestation where, the device and the verifier and the prover are far away from each other, then unfortunately software attestation is not a good solution. Okay. There are other challenges in the system. There's a very nice paper, it's a fairly old paper, but they actually talk about various different attacks. So for example, I told you that if I want to do an attestation in the entire memory, the idea is that the adversary cannot hide their code. These guys, for example, show that the adversary can create some form of a hook where whenever the attestation routine will be called, they will delete their malicious code from the program memory. So this hook basically deletes this, copy this into the data memory, and then start running the attestation. Whenever the attestation is done, then there is a second hook in the stack that copy this back into the program memory. So they show that this is actually possible, and the time it adds is as small. So for some networks, this can be actually quite successful. So there are like attacks like this that can happen. The second attack is what we call a proxy attack. So for example, you mentioned that, what if this prover managed to, make the clock faster, right? But usually that's not possible because of the physical limits of the device. But what the adversary can do is that if they can find a proxy that happens to have much faster clock, instead of like actually computing things here, they will just forward the request to the proxy. Proxy quickly computes the response, send it back to the prover, and the prover send it to the verifier. The idea is that if this time plus the time that the proxy do the computation is much less than the time for the prover that does the computation, then this attack will be successful. Okay. And again, nowadays, given that you have access to this high-end systems, this could be possible. So for example, you're expecting that your security camera is running the attestation code. In reality, though, the security camera is connected to some server or some other malicious device, and that device is the one that does this proxy. Okay. So what are the solutions for these kind of attacks? So for software attestation, as I said, one solution is using this lower jitter networks and ensuring that proxy attacks are not possible. You essentially do the attestation for all the devices. A more common solution is doing what we call a continuous attestation. So essentially, you keep the device busy all the time that they cannot use any time or a slack to send the request to another device. So this paper is talking about what we call a continuous attestation, which the idea is that we do the attestation one time, Then we send another nonce and another nonce and another nonce, such that the adversary cannot really use any time during this process to send the request somewhere else. Because if they do, then that will be amplified by each time we do the attestation. This is very similar to the distance bounding algorithm that we discussed in the class. If you remember, we also did that like many, many times, and we said that essentially by doing doing that behavior, we kind of receiving the average behavior. This is very similar. Of course, uh, um, the trade-off here is that what used to be one-time attestation is now many-time attestation, which means that your prover is now, has more energy consumption and it's less useful in during that attestation time. So there will be a huge downtime for your prover, which may not be a good thing for many systems. For example, think about a real-time system that needs to also take care of some other stuff. And then you're keeping it busy for the attestation. So basically the device itself is out of commission for a very long time, which is not great either. Any questions here? Yeah.
I guess with the system, like, is there any time for the device to actually do what it's supposed to be doing?
Yeah, so
Like, is it like it looks like it's just getting verified to like
well, the idea of attestation is that you have to run attestation occasionally. So for example, you do it every day, like during the some specific time. During that time, there will be a phase of this, but this is, for example, let's say if each one takes, let's say, 10 milliseconds and you run this 100 times, then the device will be out of commission for 1 second, but after that, it will be useful. Okay, so that's kind of the idea. But you're actually talking about an interesting thing. There is I have slides in the in the rest of the lecture, but there is this problem called time of check, time of use attacks, or TOOC2. So the time of check, time of use attacks is exactly this problem. That I run the attestation, I get the results. Let's say my attestation is actually very secure and great. Nothing bad happens during my attestation. So I get the response and now I trust the system, right? But since I cannot run the attestation all the time, because if I run the attestation all the time, it means that the device is basically not useful anymore. I need to have some kind of windows between my attestations, right? So I run the attestation at this time, maybe it takes 1 second, but then after that, I trust this device. So, and then I don't run the attestation, and then maybe run the attestation in the next hour or after 1 day or 1 month or whatever. So during these 2 windows of attestation, I don't have any check on the device. While at this point, at the beginning, like right after the attestation, I trust this device. But remember, this device is going to interact with the physical world. It's going to run code that might be potentially unsafe and all. So sometime during this period, there might be a memory safety attack. There might be a buffer overflow. There might be return-oriented programming. Because remember, attestation doesn't close those type of attacks. It just tells you that the content of your memory hasn't been modified. But for example, somewhere here, you might click on some link and download some files that you shouldn't, and so on and so forth. This is what we call the time of check, time of use. So this is the time of check. During the time of check, I know that my system is trusted, but during the time of use, unfortunately, my system is vulnerable to attacks. Okay. And if you remember, you talked about solutions for that. For example, we said that, oh, if you want to close the memory safety during runtime, we should use things like shadow stacking or make sure that our code is not vulnerable and so on and so forth. But they come with their own overheads because they are constantly on. So you're paying that penalty of memory safety all the time, versus attestation, you can run it as low as you want. So you can run it once every year, or you can run it every hour. That depends on the criticality of your system. All right, so kind of summary. Software attestation, it's very versatile, very low overhead, doesn't rely on any sort of hardware. It can run on any system, virtually any system. But of course, it's hard to achieve security because it has restrictions. For example, it cannot be working on systems with high jitter. You have to be careful about proxy attacks. You may need to keep the system busy such that it cannot forward the request and all. It's also vulnerable to these attacks where you might hide your code somewhere else in the program and then keep going back and forth. So it's useful for some systems, it's not useful for all systems. To kind of further improve software attestation, a lot of working on what we call a hybrid attestation, as I mentioned it before, which the idea is that can I use a little bit of hardware? So I don't want to go fully hardware, which is also very expensive for low-end devices, but maybe I can have a small component, okay? So I kind of balance between the security that a hardware-based solution gives me versus the low cost and low overhead benefits of a software system. So that's what we call a hybrid attestation. So what exactly do we do with hybrid attestation? The idea of hybrid attestation is that we still have our verification code. We still have our verification code and our application code. But here's what we do. So we add some form of a support or some form of monitoring or checks or trust to our system such that the adversary cannot change or do anything they want. For example, if we put the verification code in some form of a read-only memory, in other words, we ensure that our verification code is always trusted and cannot be modified, then lots of those problems that I said about, oh, the adversary can move things and the adversary can use a proxy, they're all gone because we always trust this, okay? All we need to do is just call this function, and this function will compute the hash of the application code for us, and it will send us the response, right? So the problem is now significantly easier to solve because essentially I'm guaranteeing you that this verification function is always correct and it always runs correctly. All we need to do is that now ask the verification code to hash the rest of the functions for us. So compared to hardware attestation or hardware's hardware only attestation, in hardware only attestation we put everything in hardware and does everything in hardware. In hybrid attestation, we only say that only we trust and we put a very small piece of code into the hardware. That's our verification code. We make sure that we can run this verification code correctly and securely. The verification code does the rest for us. We basically run any sort of hash function that we want for any application code or other part of the memory and send the response. In order to make sure that indeed the verification code is the one that's running this, we also need some form of a secret, okay? So we need to have some secret key to sign whatever response that we are sending. Otherwise, the adversary can does this. So if you send a request, if anyone can compute the response, the adversary never calls the verification function. Basically mimic the behavior of the verification function using their own malicious function that is stored somewhere here. So the response will be computed by this guy, and then will be sent to the verifier. The verifier thinks that it gets the correct response, but in fact, the response is computed by the malicious function, okay? So in order to make sure that this is not the case, we usually MAC the response. So not only we compute the hash, but we also sign it using our secret key. So we send the MAC of the response and not just the response, okay? So now I need a secure key, and my secure key also has to be stored somewhere that the adversary cannot access it. So these are the hardware support that I need to add to the system, okay? So I'm moving the attestation code to a read-only memory, so I need some form of a memory protection for my system, which means that the attestation code, the verification code cannot be modified and can always be trusted. We can run it on regular system. There's nothing secret about the attestation code. We just know that it cannot be modified. So that's the main thing about the attestation code. And now my hash function is a keyed hash function, okay? So not only I just compute the hash, I also need to sign it using some form of a secret. Otherwise, the adversary can also does that, which means that the adversary can lie in this process. Yes.
How do you make it so that only the verification code can find the key?
So that's where the hardware support comes into the play. Okay, so essentially, so this is kind of like, the very first paper that kind of like does this, called SMART. So as you can see, the design is that you have your kind of CPU here. Okay, you have your bus here, and this is your memory. So those darker color ones are the attestation code and attestation key. Okay, so you only make sure that your attestation code and key is stored in RAM. Okay, and can only be, and then the second thing that you need to make sure is that only the attestation code can read the attestation key. Okay, so you basically check the PC or check the or check the code and make sure that whoever tries to read that address that the key is stored is blocked unless that code belongs to the attestation code. Okay, so this way we make sure that the key is always secure. Make sense? Yeah. So the rest is the same. So you still can have your SRAM and your flash. Everything else can be stored there. But essentially, you need to kind of change the system. So you need to change the memory such that you have the key ROM and the attestation ROM. Again, SMART is the name of the paper. That's why it's called SMART ROM. And then this memory backbone, essentially your bus, should be designed such that not everybody can read that key. Only the code, any instruction that belongs to this region should be able to read this key. Anyone else tries to read that address will be blocked by hardware. Okay, that's why it's hardware software code design kind of thing. Okay. And then, by the way, many of these features already exist. So many systems comes with ROM, many systems come with memory protection and all that. So it's not like, we're inventing these concepts. We're just reusing them in many systems that already exist in our hardwares. This one is like a very low-end device. It's an MSP 430. But more high-end devices actually have additional security features that can be used as well. Questions? Mark. So big concern about the system is when the attestation ends, or if this process is somehow interrupted, we need to make sure that the system, like, the memory and the stack and the heap and anything else is completely wiped out clean. Okay, so for example, let's say I have a process like this that I run my normal code, right? So my app. And at some point, I decided that I need to run the attestation. So the request for attestation comes here. So the challenge comes here, okay? So at this point, I will finish my app and then start running my verification code, okay? The verification code is basically a keyed hash function. So it's gonna read the memory, right? So this is your memory. And then it's going to basically, get the value, compute some hash, and in order to compute the hash, it also needs to read the key, right? So it also reads the key. So during running this function, I read the key one time. I have the key in the context of this function. So for example, I store the key in the stack, okay? But once this verification function ends, or for example, if there is some form of an interrupt, or a DMA request, direct memory access request, or whenever this process just completely ends, and I want to run another application, like application number 2, I have to make sure that the application number 2 cannot access the key anymore. So not only any request for reading the key has to be blocked, I also need to sanitize the stack and any sort of, temporary memory in the system. I need to delete all the registers and clean all the registers. I need to clean my stack and heap and so on and so forth. So that's an important part of any attestation. You cannot just context switch back and forth between applications, because if you do, then a malicious application can also indirectly read the keys. Okay, so that's very important to keep in mind. So this is why we usually have what we call a secured reset. So whenever there is any sort of request from the PC, from the interrupt, the error also goes into this hardware monitoring unit that caused the system to reset. And this reset is basically cleaning up everything, deleting everything from the registers and the stack, and then resetting the system. So essentially like, repeating the attestation process or any other process, like initializing the boot and all that. So the design of the system, essentially like the full design of the system will look like this. So you have your core. You have your core. You have your kind of memory backbone, which is your bus. Remember I said that there is a software attestation code in the ROM. You also have your key in the ROM. Then in your RAM, you might have your, apps, but you might also have the stack, right, for the software attestation. And then you might have other things in your flash. What you add to the system is also some form of a hardware support, that what it does is does this monitoring. So you basically look at the behavior of the core. If it sees that it tries to change the program, it tries to, read the key, any sort of attempt to break the assumptions about the system will result in the reset function. So it doesn't allow the system to do that. So it resets the function. Of course, this will be vulnerable to, for example, denial of service. The adversary can basically continuously try to just read the key, and anytime that it tries to read the key, the system will reset. But there are other ways that you can actually even prevent that from happening as well. For example, there are papers that shown that if I see reset multiple times, I can, for example, store reprogram the system or have some form of a contingency plan that if I see multiple resets, I can prevent that reset from happening again and again and again, and so on and so forth. So there are ways that you can even prevent that from happening as well. Make sense? So as you can see, what I'm changing here is very tiny thing that basically just do very simple monitoring. That's why this is a hybrid method, that most of it is really still software. Most of it is just having the software attestation code and running it on the CPU core. So that software attestation is exactly similar, the same code that we had in the software attestation. The only thing that we are changing is that we don't let this code to be modified because it's in ROM. Second thing is that we make it keyed and only allow the key to be accessed by that software attestation code. And the third thing is that anyone who tries to kind of tamper this process will be detected and will cause a cautionary reset to the system. So essentially, any attempt to read the key, change the values, and so on will be blocked by this hardware module. Okay, so that's kind of the key idea of a hybrid attestation. As I said, neither of these systems, nor the software attestation or hybrid attestation, is secure against TUK2 attacks. TUK2 is the time of check, time of use, which essentially means that if we attest at time T or time X, we don't know anything about any time in future, okay? The only thing attestation gives you is that at the current time, you know that the system is secure, okay? So it doesn't matter whether I'm using hybrid or software, we're still vulnerable to this attack. There are various different solutions about TUK2. As I said, for example, you can do continuous attestation. In some cases, you can monitor the memory between checks. You can execute things right after attestation, and then once you want to switch to another app, run another attestation. You can randomize the check such that the opportunity for the adversary to do the attack is much less. So there are tons of different solutions that different people have thought about. Eventually, there is no guarantee for Tuk2 unless you do some form of a runtime checks. But there are ways to reduce the chance of a Tuk2 attack if you want to. Okay. Any questions at the moment? Good. All right. So to finish the design of hybrid attestations, I'm going to present a recent paper that we published last year by my students. So the idea of the paper is called a hybrid attestation that supports interrupt and Tuk2. I'm going to explain what's the problem we're trying to solve is. So kind of to summarize what we learned so far is that we have software attestation and hybrid attestation. In software attestation, essentially, you kind of read some part of the code, some attestation code, and you time it, and you basically trust the system if the response is correct, is the expected response, and the time it takes to compute that response is less than a threshold. This is the premise of a software attestation. In hybrid attestation, what you have is essentially two pieces of memory. You have a ROM that has your software attestation code. Since it's in the ROM, you no longer need to check the attestation code. And then you will add this hardware monitor that basically checks the behavior. The big thing is that you have this key in order to produce the response, and you will trust the system if the response is correct. You no longer need to check the time, right? So the big difference between hybrid and software is hybrids, if you get the response and the response is correct, you're good to go. And if there is any attempt to kind of tamper this behavior, there will be a reset signal issued to the system, okay? If you remember, I told you that the biggest problem in this system is that we need to be very, very careful about the key, because if there is any sort of interrupt or any activity other than the software attestation trying to access the key, then we need to clean up, right? So we need to do reset the system or clean up the system and then give the access to the system. This means that if during the attestation there is a very important task that needs to be run, let's say this is a real-time system, for example, think about a car or a vehicle that needs to, for example, make some very quick decision at the same time you also want to run your software attestation, then you will basically, this becomes a dilemma between should I do the main functionality of the system or should I do the attestation? In most systems, the solution is that you stop the attestation, you service the important things that you need to do, then you reset the attestation and restart the attestation, okay? So this is what we call, this is what we have in the past prior to this paper. That essentially we call that the attestation has to be atomic, which means that it has to be uninterrupted. If you really, really need an interrupt, you just redo the attestation, okay? Which works fine. In terms of security, there is no issue with it, but it's a big waste in terms of power and performance and attestation time. So the idea that we are trying to fix in this paper was, can I pause the attestation, do the interrupt, and then come back and resume the attestation? So I don't want to restart the attestation. I want to resume the attestation. So how do we do that? Essentially, so this is all the explanation of what we do. So essentially, if I want to do this, I need to basically taint and track and sanitize the key, and I need to remove the key. This means that there is no support for interrupt and DMA. DMA is, how many of you know what DMA is? Okay, few of you. So let me then explain what is DMA before explaining the rest. So DMA is like this. So let's say, for example, I have memory, okay? Then I have an IO, okay? So for example, let's say this is a USB drive, okay? And then I have my core here. So let's say I want to read a big file from my USB, okay? The way it works is that without DMA, the process is like this, that the USB will send the data to the core bit by bit, then the core will send it to the memory because core is the only one who can talk directly to the memory. Other components cannot talk to the memory directly. Okay, this means that if I want to run if I want to save, read or write a big file, essentially I need to keep my core busy all the time because essentially core is the one that take the data from here and send it to there. Okay. So in order to fix this, we usually have this extra additional component in our system called direct memory access or DMA. That what it does is that the first time that USB or any other I/O component wants to read or write from the memory, they send a request to the CPU. Let me show it with a different color. They send a request to the CPU. The CPU will configure the DMA, basically says that, oh, this guy will send you some data and it will be written to this part of the memory. So we'll configure this DMA using the configuration register that DMA has. After that, you no longer need to send the request to the CPU. You can just directly send the request to DMA and DMA will forward it to you. Okay, so think about the DMA as some form of an agent that understand the request. This means that the core no longer needs to be involved in this process. The core only knows when this process begins and when this process ends. Okay, and this is a standard in almost any systems, both embedded and high-end systems. So your laptops and your high-end system has this, your low-end system has this, because this is a very important thing to have. So essentially, DMA requests will issue an interrupt to the core. That's why in the context of attestation, DMA request is no different than your regular interrupts. Both of them will create an interrupt. The process needs to stop, needs to handle the request of the DMA, and then needs to come back and continue. But since in embedded system and IT systems, DMA requests are very common, we need to be able to handle them. Otherwise, we're going to miss the data. So for example, think about a Bluetooth module that receives a lot of data and needs to actually send this data to the memory. It needs to save it. Otherwise, you're going to miss it. So it needs to be able to handle DMA requests as soon as possible. So with attestation, I can do that, but that means my attestation needs to be resetted. I don't like that. So how do we do that? How do we fix this issue? We introduced this model that we call interruptible dynamic attestation, IDA. The idea of interruptible dynamic attestation is this, that I don't need the key for during the attestation, okay? Since my monitor basically monitor the computation of the hash, I will use the monitor to check whether I'm actually computing the hash or not. Then only at the end, once the hash computation is finished, I'm going to use the key to sign it. So the hash computation now is just a regular hash function computation. It's like a SHA. It's no longer an HMAC, which means that anybody can do the hash function and there's no secret involved. But in order to make sure that this hash function is indeed secure, we're going to monitor it using the hardware. So basically, we're going to use the signals to make sure that this hash function is indeed run by my ROM and not by other part of the system. But then once the response is ready, once the hash computation is finished, then I'm going to sign it. Which means that if during the hash function computation, there is an interrupt, there is no secret to protect. I can just basically pause the hash. I can go and do the interrupt and come back, okay? There's one interesting thing that I need to be worried about though, and that is that if the adversary basically does this, so for example, if this is the memory, and this is the part that I've already hashed, okay? If during the interrupt, basically the adversary goes to the interrupt and does something like this, that during the interrupt service routine, they kind of go and change things here. Since I'm resuming my attestation, I never go back and change this, check this part, right? I'm gonna basically check the rest of the memory, right? So the adversary can change the previous parts of the memory without us checking it. In regular attestation, since I'm resetting the whole process, I'll check everything. So I don't care what the adversary does even during the interrupt, because during the interrupt, they can change everything they want. Since I'm going to run the attestation again, I will detect it. But with our system, since it's going to resume, then that will be a problem. So how do we fix it? Our solution was that we're going to monitor the memory writes during the interrupt process. If the interrupt wants to write anything to the memory, then we reset the attestation. If the interrupt does not write anything to the memory, then we can safely resume the attestation. Yeah.
Interrupts almost always write to memory though?
No. So for example, interrupt wants to read data from IO to do some activity. So for example, do some some detection or some behavior. It doesn't need to write to the program memory, right? It writes to the data memory, change the data.
The data.
Yeah.
They just monitor the program memory.
Yes. Yeah. So you can have your stack changing, all that, or registers. You can write to all of that. That's fine. But if and again, it can write to other part of the memory. That's fine. It cannot write to the part that we already checked, right? So the chances are very low that they write. But if for some reason they really need to write to that part of the memory, then we just go back to the original format and we just reset the computation. Say, okay, if you want to change the memory, then change it. We're going to go back and reset the process.
Why would you ever write to the program memory anyways?
Because you want to update the code. You want to inject things. You want to update the firmware. There are different reasons that you need to update the program memory. Yes.
If the hardware monitor is actively checking the hash, can you remind me why we need to sign off with the secret key at the end anyways, if it's making sure that what's happening is coming from the wrong?
Well, we need to tell the verifier that this process indeed happened, right? Okay. So that's the only reason that you need to sign off that. You don't necessarily need to sign off even the hash. You need to sign off something and send it back to saying that, okay, we did this and trust us. So you can, for example, also sign off the challenge and send it back. In order to make sure that this process cannot be repeated, you usually sign off the hash function. Okay. So this is basically what I described. Essentially, the idea is that we're going to do a monitoring, we're going to do hashing. The hashing is run in the untrusted word. The authentication only happens in the end, and that's when we send the response to the system. So, like, now we have two phases. The hash computation, no secret involved. We call it authentication of the response, and that's where the secret is involved. The second thing that we do is that since we have this capability of monitoring the memory during the interrupt, we expand this to Tuk2 attack as well, because essentially what Tuk2 does is we are saying that we have memory, right? And we compute the hash over this memory and send the response, right? At the end of the attestation, if I trust this response means I trust this memory, okay? The problem with Tuk2 was after this time, if the adversary go and change part of this memory, then my system is compromised, right? So here's what we're going to do. We said that we already have the capability of checking what has been written to the memory, right? So if I can do that, then essentially what I can do is that during this time that I don't run the attestation, I'm going to continuously monitor the writes to the program memory. If I observe any writes to the memory, I can issue a new attestation myself. I can either auto issue it, or I can request the verifier to send me another challenge. If nothing happens during this time, it means that I'm guaranteed that I'm still safe, because I checked the memory. The last time I checked the memory, nothing has been modified. I haven't observed any write to the memory, so it means that I'm continue to be safe, right? So this way of continuous monitoring the memory writes and doing the attestation once, then all you need to do is that if a new request comes here, if nothing has been written, you can just repeat the same hash that you had before. So this is also saves you a lot of time. Of course, you can change the challenge but generally, if it comes from, if it's signed by the hardware, you can show that this continue to be secure all the time. Does that make sense? Any questions? Cool. So essentially what we have relaxed is we no longer need atomic execution of the attestation code. We allow the attestation code to be invoked. We don't need the reset to be always, issued if there is an interrupt, and we can allow any sort of DMA monitoring or interrupt monitoring during the execution. I recommend you to look into the paper. We have the implementation and some security analysis on all that. To save time, we can just skip it. But generally, this is kind of like the design of our hardware module, which has an HMAC, which has the key, and then has just a general monitoring logic to check whether or not something has happened during the system. So this is the part that we are adding to the system. This is the hardware part that we are adding to the system and to the software attestation. And essentially what we are monitoring is the PC, the memory address, the interrupt request, or the DMA write, and there is some form of a shared status register between the CPU and this hardware module. And then we have, some final state machine that is like monitoring and interrupt and ending and invalid and waiting. To save time, I'm not going to explain any of these, but if you're interested, definitely check out the paper and you will see we have the algorithm and all that, which let me skip all of that because we don't have time to go over it. Let me show you some results. Does anyone have any questions about the details that I said to you about the TUC2 and the interrupt and atomic execution? Okay. And by the way, we call the regular system IDA. The IDA plus is the part that is also support the TUC2, which means that the continuous monitoring after the attestation has been finished. So this is kind of two part of the same idea. So essentially, if you make these changes, you kind of need about 4 kilobytes of a ROM to run this attestation code. That's about 3% of a memory of like a small MSP. So that's very small. The hardware that you need to add is about 20% of an MSP. So if you think about like the core and the memory and the logic of MSP, those things that I show you is about 20% of it. We kind of compared it with some other papers as well. If you're interested, you can check that out. And then the attestation time essentially is significantly less than other methods because hash functions generally is much faster than MAC functions. MAC function is twice as slow as hash functions because you can think about an HMAC is hashing a function twice. That's why it's kind of like, HMAC is generally twice slower than hash function. So one benefit of our approach is that since the majority of time is hashing and only one time we are macking, we're actually getting twice as fast attestation time compared to the other methods that just do the hash and then do the HMACking all the time. So that's also another benefit of the system. With all these, you're gonna get about 20% runtime overhead. So someone asked that, would the system have time to do other things? Yes, 88% of the time it does other things and only 12% of time can do attestation. Of course, this is also a function of how frequent you want to run your attestation. But with the TUC2's guarantee that you have, you know that your system will be always secure. You don't know whether or not you trust this device. That's a separate story. But if you run the attestation, I think every hour or every 2 hours or something like that, that would be the overhead of the system that you're going to face about 12% of the time. All right, so that's kind of like the summary. the key idea is that now you can resume and replay the attestation, and this is kind of the state of the art. So actually, this paper that we published was last year's, and there hasn't been any paper after this yet. So this is kind of the state of the art in the attestation domain. One thing that you might also wonder is, does attestation fix the issue of code reuse attacks? And the answer to that is no, because attestation is only fixing and checking whether your program has been modified. If you use the existing code in the program, attestation is not going to fix that problem. So attestation is useful for code injection, but it's not helpful for code reuse attacks. So how do we fix the code reuse attacks? There is also another thing called control flow attestation. This is a runtime attestation, which the idea is that we don't check the status of the memory. We can check the status of the memory, but we also can check the control flow. So basically, what we do is that we hash the basic blocks that we pass through. So for example, you give me an input, I run the program, I go through different parts of the CFG, right? The control flow graph. What I can do is that instead of hashing the memory, I'll hash the basic blocks. I say that, okay, this is the first basic block that I passed, this is the second basic block, this is the third basic block, and I send that hash back to the verifier. Now the verifier can basically check which basic block has been traversed in this execution, and they can see whether this is a legitimate traverse of the basic block, or has there been some basic blocks that it shouldn't have been visited, okay? This way, we can protect the system against both code injection attacks, because I can always check the hash of each basic block, and I can also protect the systems against code reuse, or generally any sort of control flow hijacking attacks, because I know exactly the sequence of basic blocks has been checked. But keep in mind, this does not prevent, this only detects. So it's after the fact. So you only know that the result that's been produced by this is not trusted because there has been a control flow hijacking. If I want to enforce this in runtime, I have to use CFI methods and shadow stack methods that I described last time. So this is different. So this is only just hashing things. This happens in the background, so it's much faster than CFI, but it only tells you that something happened. It doesn't prevent that from happening. Okay? There are tons of challenges. There are, of course, overheads. Now you need to check every basic block. You need to hash every basic block, and think about a gigantic program that has many, many basic blocks. Your hash function computation would be huge. But there are papers that shows this, and there's also, this is a continuous area of research. This is called CFA, control flow attestation. So there's like a regular attestation, which just checks the content of the memory. There's a control flow attestation that attests the control flow. There's also control flow integrity, or CFI, that does this in runtime, which is two different things. So don't be confused by the terminologies. All right, so that's it for attestation. Any questions from attestation? Yeah.
So how's this different from CFI? Like one is run at runtime, the other one's like before runtime, or?
No. So CFA is basically all it does is you send a challenge, which is an input to a program. You let the program to execute fully. You just hash the control flow and send back the response, which is the hash of the control flow. Okay. Now the verifier will check that hash to see which basic blocks did you run. So essentially, it's recreating the basic blocks that have been executed. Okay. So now it checks whether these basic blocks are the correct basic blocks from this input or not. If it is, then I can trust this execution. If it's not, then it means that at some point during this execution, something happened. So this has jumped to some other basic blocks that it wasn't supposed to. So this is how it's protected.
Like an on-demand CFI, or like.
It's an on-demand CFI in a sense, yes. But again, it doesn't prevent this jump from happening. It just tells you that this jump has happened. So it's a detection mechanism. It's not a prevention mechanism. Good?
Yeah.
Any other questions? All right, let's have a quick break and then we're going to talk about the last thing.
I think that's like this thing.
Okay.
Every day.
Last.
Actually.
All right, so it's kind of continuation of this attestation, control flow integrity, control flow attestation. I want to very briefly talk about isolation and trusted execution environments. Since we don't have much time left, the discussion will be brief. But if you guys are interested, I can show you, I can link some papers and you can read about it. But I felt like to make the whole story complete, it would be helpful to talk about trusted execution environments as well. So if you remember, like we started this class by saying that the very first step in making sure that our devices are secure is booting it securely. And in order to achieve secure boot, we had this trusted platform module TPM that has a little bit of hardware and a little bit of software that reads a tiny piece of code and hash it and then make sure that it's correct and use it to bootstrap the trust and eventually creates the OS, like it loads some form of an operating system, or in lower end devices, this is usually a real-time OS, or even in lower devices, it's like some form of like a simple firmware, which is just a flat, memory application. So in any case, you will check that, you check the kind of hash of that, make sure that this has not been modified. You load this and then you start executing it. And that's where we start our kind of, exploration of various different things can happen. We first talk about different attacks to the sensors and faults and all that. Then we talked about memory and memory safety and checking the memory safety and fixing the memory safety and all of that, right? But the idea that we are going after now as to kind of finish the discussions is that what if there is some form of an inherent bug or problem in your system that even when you're loading it, the system is already compromised. Or you have reasons to believe that the system is not trustworthy. For example, you don't necessarily trust the system as is. You want additional guarantees to trust the system. This is where trusted execution environments coming. So the idea is that we are assuming that the OS or the software of the system is fully compromised. Can I still run some application in this system securely? And this is what we call a trusted execution environment, or T. The idea of T is that we're going to have some form of an isolated environment. We usually refer it as to an enclave that allows you to run things separately from the OS. So you can think about an enclave as a computer within a computer, that essentially we have this smaller environment, this trusted execution environment that lets you to run some programs, some arbitrary programs in an environment, bigger environments that is not trusted, okay? So why this is a good idea? The reason that this is a good idea is based on this principle that smaller code is less buggy and less prone to attacks, okay? That's why I still can have like a very large operating system, like for example, a Linux that has thousands and thousands of lines of code. But instead of like relying on this to handle everything for me, I'm going to have a smaller OS, which we usually call trusted OS, that is very, very tiny. So it cannot do all the fancy things that the operating system can do. Maybe it can do very little things. And then it also has maybe tiny memory and tiny processor. But this is inside this bigger thing. And some of my critical applications will run on that trusted execution environment and that tiny environment. And I still use my more rich environment for all the other less secure things. Okay. Ultimately, you want this to be one, but this is more of like realizing that I cannot really fix this. So let's actually find something that I can work with better. Hopefully, once we have, better software solution and all that, this can be this, and we can have one uniform secure environment. But for the moment, if I want to use, for example, a legacy system and a trusted systems, that's how we're going to do it. Okay. So what are the ingredients for this? Of course, you need to, for this to work, you need to change both hardware and software. There is no pure software solution for this. So you need to make some software changes and you need to make some hardware changes. So the very simple idea is that I want to expose TPM to the external world because the user has to be able to run program on this hardware. If this is a purely isolated hardware that nobody can run anything to it, that's also not going to be useful, right? So I need to expose this. So I need a software tool chain for this as well. So I need some layer of operating system, some user level, so that the end user can actually run some arbitrary software on the system. So on this software changes that I need to change is essentially I need a paradigm to run arbitrary code. And this is very similar to the same paradigm that we have for the operating system. So those of you who know operating system, have taken operating system, you've probably seen that how we actually run code into a hardware. There is some form of a system software, create a process, save memory spaces, assign locations for the code and data and all that. So you need similar things, but now you're kind of duplicated this for trusted and untrusted. But keep in mind that everything that we do in the trusted domain has to be minimal and small. So essentially what we call is a trusted computing base or TCB. TCB has to be very, very small. So we need to get rid of many of the capabilities that a normal OS has. So for example, inter-process communication, multi-threading, synchronization, file system, all that is usually gone in a trusted operating system. Trusted operating system should have minimal capabilities. For example, it can only create a process and delete a process, or it can maybe support some very limited system calls, such as, and it can support a simple int route, or maybe it can read and write to a particular peripheral and things like that. But so it's essentially you kind of strip down the operating system and kind of keep the core functionalities and you get rid of the rest and hoping that the bugs does not exist in the system. Again, there is nothing guaranteed in a trusted operating system that is not there's not bugs in it and there's no problem in it. But the idea is that since it's much smaller, the designer can actually verify it. They can use all those static tools that we described in the class. They can use manual, tricks to actually check every line of the code. Versus if you want to check Linux, for example, it's almost impossible to check every single functionality. It's very complex that it's not possible to do that. Okay. So in order to do this, we typically have what we call a secure monitor or SM. So this is a layer that goes, lower than your regular operating system. Essentially, what we do is that we're going to have runtime environments that each application can. There is food outside.
There's like a graduate.
Wine outside.
Yeah, there's a graduate thingy going on.
Wow.
Wine.
Interesting.
Peas.
I'm gonna finish the class sooner so you can go.
It ends at 6 of them.
Oh, I mean, I can finish at 5:45. All right, anyway, so you can have much smaller OS to finish. So let me actually show you the picture here. Actually, let me show you the hardware changes and I'm going to show you the picture. So in order to support these software changes, you also need to change the hardware. So what you need to do is that you need to kind of differentiate between activities that is relevant to the trusted domain in your enclave, and activities for your normal operation. So you need some form of checking and some form of a separation or isolation between these two activities. Okay, so to give you an example, so there is bunches of these different trusted execution environments. I'm going to quickly go over trust zone as one of the examples, but there is other things such as Intel SGX, there is ARM AMD SEV, there is RISC-V based trusted execution environments. So there are different ways of implementing this. There's no one implementation, but since we are in the IoT domain, the common one and the most dominant one is ARM trust zone. So what is the concept in ARM trust zone? The ARM trust zone divide the world into two worlds, a normal world and a trusted world. Okay, you cannot go beyond this, so you cannot have multiple trusted world that they don't trust each other. There's like everything in trusted world trust each other, everything in normal world trust. Well, essentially, in normal world is like nothing trust, no one. There's no trust exists in the normal world, but in a trusted world, you trust everything. Later on, ARM came up with the idea of CCA or confidential computing architecture, which then allows you to have what they call realm instead of word. So now you can have realm, which each realm don't trust the other realm, but they trust everything within the realm. But for now, we go with the simpler one. The realm one hasn't been even implemented yet in commercial systems. It's something that is coming in 2026. But the commercial system, this is actually commercially available in many ARM cores, is the trust zone, which you have what we call a rich execution environment, RE. This is your regular system with Linux operating system or Windows or whatever you want to run it. If you have an A series, if it's the M series, it's probably you have like a real-time OS or like a simpler operating system. And you have a trusted execution environment or T, okay? T can access all the resources in RE, but it's not vice versa. So trusted apps can do whatever they want, both in T and RE. Of course, you have to be careful when you're going to the RE side because nothing is trusted. But RE obviously cannot access things in T, otherwise it defeats the purpose. And apps in T's, they have to trust each other. Unfortunately, there's no way that they don't trust, there's no way to block them. So in other words, if something is wrong in one of the apps in T, it's basically compromise the entire T, and that's one of the main limitations of ARM trust zone. This is how ARM trust zone looks like. So essentially you have the non-secure world or normal world, and you have the secure world. In your normal world, you can have many apps, and you will have your rich OS. In your secure world, you're going to have your secure OS or trusted OS, or different terminologies. Then you have a bunch of trusted apps. As I said, you will add another layer of abstraction called secure monitor. The secure monitor allows the communication and transition of the trust between these two. You cannot rely on rich OS to handle the transitions because the rich OS is not trusted. So you cannot say that, oh, rich OS, please switch to the secure OS. That secure monitor is the level that kind of captured this trust. So secure monitor is the highest level of trust in your system. Typically, we show it with like, level. So this is usually goes to level 3. This is level 1. And this is level 0. So this is a layer of trust. The higher numbers means more trust. There's no level 2. But as I said, CCA later add a level 2 so that it allows you to separate the rich OS from each other. So there is one, a secure OS. There is one secure OS that handles everything. In newer models, this secure OS is also further fragmented. Okay. So how does the system work? So essentially, you can start by running code in your non-secure world. If you want to switch to the secure world, you will execute a branch, a call. It's usually called SMC, system call. This SMC then goes to what we call a secure API. The secure API allows you to call functions in the secure domain. We cannot call arbitrary functions from non-secure domain because that obviously is a security vulnerability. So non-secure can only call very specific system call, which will be captured by the secure monitor. So this part is where the security monitor will come into the play. It will basically then calls whatever function that you want in the secure world. This is all the libraries that you might have, all the system calls you might have that can be only accessible by this secure API. So this is usually what we call secure, non-secure NSC or non-secure callable, which means that it can be called from the non-secure world. So you can run these codes here as part of your secure world that can access to some libraries that are secure. So for example, if there are some particular functionality that you want to collect and do, and then once you run these things, and then at some point you can then jump back to your normal world. And this jumps can be directly from the secure environments to non-secure because you have the trust from secure to non-secure. Essentially, if you think about how this is implemented in your system, you will have your processor here. Everything, including trusted and untrusted, is running on the CPU. I'm not duplicating the CPU, but what I'm doing is that I'm fragmenting and dividing the memory into a non-secure part and a secure part to make sure that secure part can only access secure part and non-secure part cannot access secure part. I'm essentially doing this hardware unit called trust zone control access TSC that I'm going to describe later, that basically doesn't allow accesses from secure non-secure world to the secure world. Okay, how do they do that? They essentially just add 1 bit to every memory, which 0 means, for example, non-secure and 1 means secure. So the only thing that you need to do is just checking that bit. All the ones can be accessed ones and zeros. Zeros cannot access ones. Okay, so that's all you need to do in trust zone. So in terms of implementation, there are 2 things that is happening. One is we need to enforce this control, this access. This is, as I said, this is what we call a trust zone address space controller, or TZC, trust zone controller. Basically, what it does is that every access to the memory is checked by that 1 bit. If that 1 bit is not a part of the secure world, it will be blocked if it's running by a non-secure. You have a question?
Yeah, what's between this and like regular like OS, like kernel mode versus like, regular user mode process, like, stuff like that.
Similar idea between kernel mode. There you have to trust the kernel. So this is, you don't trust the kernel. This is a separate kernel for that. But it's a very similar idea.
Like a third.
It's a third, yes. So that's why you have 3 level of trust. So now you have E0, E1, and E3.
Okay.
Yeah.
Well, I thought you said at like the start that like the point is that it's sort of like a separate hardware component. Because like, yeah, that's the difference between like this idea and like user mode and kernel mode. I'm not.
So the hardware part allows you to achieve this 2 separate world, right? So essentially what I'm adding to the system is one for trust. As I said, there are different ways of implementing this. So for example, Intel has different ideas of implementing this. But in trust zone, essentially you're saying this, that your apps are either part of a trusted app environment or non-trusted app environments. And the way that we're going to differentiate these 2 from each other is that we are having this flag bit that is either 0 or 1. So the way that we change the hardware is this. At the software layer, we also have 2 OSs. We have a trusted OS, which is much, much smaller, has less functionality, but it's verifiable most of the time. So it has less opportunity for bugs and problems. And then you have your rich OS, which has many, many different functionalities, but it's also buggy and not trusted. Does that make sense? Okay. So that's one thing that you should do. So you will have this TZC, which is just 1 bit. It's usually also called memory protection unit or MPU. The second thing that you need to do is that since you have one core and now two words, you need to be able to context switch between them, right? So you need to time slice your application because there are normal word application and now there are trusted word applications, and you need to be able to go back and forth between them because there is not like you always just only runs normal word or trusted word. So there needs to be some form of a switch back and forth, as I'm showing you here, between the non-secure and secure. From non-secure to secure, I don't care, I can switch. But from secure to non-secure, I have to be very careful at. So remember I told you that, for example, for attestation, I need to do the cleanup and I need to make sure that the key is not leaked into the registers and memory and stack. Same story happened. From secure to non-secure, there should be secure context switch. It means that it has to be cleaned up as well. So it's generally switching back and forth between non-secure and secure comes with overhead, and that's one big problem and limitations of trust zone, because you cannot just switch back and forth as you would do in normal system, which you just take the copy, you copy the previous copy and you move forward. Here you need to also do additional cleanup, which is time consuming. Okay, but these are the two main changes that I'm just checking the bus and making sure that accesses are for apps that belongs to the word, and we are doing secure slicing of time and sharing the resources. Okay. How does the system work then? Then initialization is that we initialize into the secure word. So after the boot, we start the secure word. Then we give the control to the normal word. But whenever the normal word creates cause a system call, the secure monitor will take over and pass the control to the secure word again, and then secure word can jump back to the execution. So it would look like something like this, that we initially start at the secure firmware or secure word domain. We do the boot, we have the trust on initialization, then we pass the control to initialize the rich OS. The rich OS start executing application. At some point, there will be some call to the secure word, and then at some point, this control will go back to the non-secure word. One thing that also pay attention and is important to note is that secure word can have callback function in non-secure. As I said before, secure word has access to all the functionality of a non-secure word, so they can use some system calls, like for example the file system and all can be done in non-secure word. Just keep in mind that when we are relying on non-secure word, it may or may not work. So your design has to be such that you cannot rely on the fact that things are running correctly in the non-secure word, because you're assuming that the OS is compromised. So the moment that you're leaving the secure word, you cannot trust what's going on the system. So that's also the kind of the trade-off that you need to deal with. Okay. This also allows you to handle exceptions and interrupts. For example, if you're in a secure word and then an interrupt happens, you can switch to the non-secure word. That's totally fine. As I said, here it requires a secure switch. But then once the exception happens, you can come back. You can also have a secure exception or interrupt. So within the trusted word, you can also have interrupts, but you can also have nested interrupts. So for example, there is one interrupt or one exception, and there is also a non-secure. For example, you're using your phone and then your phone rang, or you want to take a picture. These are regular activities, right? So you should be able to handle all of that. You don't want to prevent your system from doing its normal tasks. So all of that is supported in trust zone. So it allows you to switch back and forth, but it comes at the cost, because you need to then save everything securely and clean things up. But it has the functionality of doing all that. How does it do it? That's a separate story that we don't have time for it. But just keep in mind that you can unlimited amount of switch between secure and non-secure. That's totally fine in a system like trust. Okay. So what are the limitations? As I said, it has only 2 words, which means that if something in the one of the trusted app is compromised, then everything will become compromised. Another thing is that access to the peripherals is very iffy. So it's usually hard. And also usually it's exclusive, which means that either the normal world or the secure world can access. So for example, if your camera is connected to the normal world, that means that secure world cannot really access it. And then, as I said, there is no principle of least privilege because now all the trusted apps has access to everything, which is not good. And as I said, ARM understood these limitations and have been working for a few years on this CCA thing, which gives you all of these things that I said, has now multiple words and so on, which is coming out very soon. There are a few other examples. For example, this is for RISC-V. For RISC-V, you have a user mode, supervisor mode, and a machine mode. Interesting thing is that you can have different types of trusted apps. So unlike TrustZone that you have just only one, you can have, for example, one enclave that has an enclave app, e-app, and a runtime. You can have another one that has another runtime. So that actually gives you this different, separation of trust. So enclave 1 and 2 does not necessarily trust each other. And the way you're supporting this is that you have the user mode, you have a supervisor mode, which has the runtime, and then you have what we call a machine mode, which still has that secured monitor. How do we actually achieve that? They have these PMP registers, physical monitoring protection registers, that allows you to say which of these belong to what. So remember, in TrustZone, we only had 1 bit. In design of something like RISC-V, you have different registers with multiple bits. So now you can differentiate, saying that, okay, this part of the memory is for SM, this part for enclave 1, this part is enclave 2, and so on and so forth. Of course, this comes with extra costs, but you can actually access things. And another thing is that then you can also, for example, for E2, you can access E1 or vice versa, right? So if you want to have additional visibility from one enclave to another enclave, you can, for example, say that, Ray does not have access to anything, but White has access to everything. So that's why, for example, E2, E1 cannot access E2 and SM, but SM and E2 can access E1. Okay, so this is like, for example, if you have tier level of trust. So E2 trusts E1, but E1 does not trust E2, and so on and so forth. So these ways we can have these layers of trust as well. There's also another example that if I want to extend it to peripherals, how can I do it? There's also this paper called Cure, which was fairly recently published, show that you can also use this to isolate. For example, you can isolate the memory, you can isolate the cache. For example, you can say that, this enclave can only access this part of the cache, and the other enclave can access the other part of the cache. So there is these things that you can do. For example, you can also, slice the peripherals, say that, okay, Wi-Fi can only access by one enclave, and display can access by the other enclave, and so on and so forth. So you can do all these tricks in the system. And then if you're interested, you can definitely read that. As I said, we don't have time to go over the full details of for the T's. And of course, T's will give you security services. It gives you remote attestation that we talked about. It gives you privacy confidential computing, ensures integrity. In some cases, it gives you availability as well. In some cases, it doesn't. And the last slides I want to show you is how do we load a program using a trusted execution environment. Essentially, the idea is that we use cryptography to basically load the code and does the remote attestation. So essentially what we do is that the first part is key exchange, that doesn't matter. At some point, I'm going to have the key, okay? Then I'm going to send my code to the enclave. I'm going to encrypt it such that the normal world doesn't see it, okay? So I'm going to have the code here. What I'm going to do is that I'm going to run an attestation in this code and send it back so that the owner, the verifier knows that the code and data has been loaded is indeed correct. So same idea of hardware attestation that I talked about happens here. Then I can do the computation on that code and send you back the results. The results is also encrypted. And then the verifier will decrypt this using the key and gets the results. This is what we call confidential computing, which the idea is that nobody but the trusted environment will see the code and data. And not only that, we ensure that the code and data never been modified. So we actually send the attestation of the code and data. So at the end, I get the data. Nobody else has seen what happens, but I have what I want, and that's all we get. Yeah.
This is more for like server embedded, right?
Yes, for example, this is we can do it for IoT systems as well, but
But like, what's the use for an IoT system? Like to give it a new function?
yeah, let's say for example you have an IoT device that is more capable. So you can send from one to another. So for example, this is your camera,
I see.
right? You don't have the capability to run it. You send it to your Jetson, does the computation, send you the results.
But if it says encrypted, how does it run? Like it has to be like self-encrypted.
No. So when you send it, you're encrypting. Here you decrypt it. So at this point, you actually have to decrypt it first. So the reason that you're encrypting it is that during the communication, you don't trust, right? You don't trust a normal world. You don't trust the communication channel. But from the normal world, you just forward it to the secure world. You decrypt it, and then you're good to go. Okay. All right. So that's it for today. And that's it for all the things I wanted to say for your exam. On Monday, we're going to go over the paper presentations, and if we have time, I might do a very quick review of the topics that we discussed. And we're gonna have the exam on Wednesday. Okay. Thank you, guys.